Ready to go on to normal? Yes, sir.
Are normal uniform painting?
No. What's the shape of a normal distribution? It's not a rectangle. It's the bell curve that's not skewed. So let's flip the page. That was a perfect segue. Thank you. Look on page 71. Look on the very next page on the top of page 71. Couldn't have paid you to ask that at a better time.
Paid,
What'd you say?
paid, obviously.
Obviously, yep. It's like the heckler you put in the back of somebody's thing. Here's my normal distribution like we talked about way back when in chapter 2, I think is when we first saw it. We saw it in chapter 2 and chapter 3, the normal distribution. Definitely not uniform. Why not? What's the shape of a uniform? A rectangle, right? It always goes straight across. This one does not go straight across. It doesn't go straight across because the things in the middle have higher, these are still probabilities, by the way. It's still like the probabilities are over here, right? Your x's and your probabilities. But these have higher probabilities to be in the middle than you would on the edges. An example of that would be the same example I keep bringing up all semester. If I flip a coin 100 times, how many tails do you think I get? 50. That's probably the thing I'm most likely to get is 50. So 50 tails would be in the middle. And getting, you know, more than, say, 80 might be over here. If 80 is over there, the height for 80, this little height here, is much smaller than the height here. The height is your probability. So this has a bigger chance of getting 50 tails out of 100 than there is to get 80 tails out of 100. It's a smaller height. That means it's less likely to happen. Is that okay with that? Okay. I'm going to take off these numbers though because I want to talk about them on the page. But they're not all equally likely. You're not just as likely to get 100 tails as you are to get 50 tails. So it has a different distribution. So it is called a standard normal. Standard normal, if we know the mean is 0, normal just means it has that shape. But it's standard normal if the mean is 0 and the standard deviation is 1. That's the definition of standard normal. And look what it even says. The total area under the curve is equal to 1. Now here's where some of you who have taken or may take calculus someday might be going, wait a minute, you told me this never touches. It goes like on forever without actually touching. Right, these get closer and closer, they don't really touch. It looks like they do on my curve, because what happens is they get so close that you can't really tell that there's a separation there. And same thing over here, it gets so close that you can't tell, but it actually never touches. But it gets so darn close that the area out past that, it rounds to 0. There is some tiny, tiny area, but it rounds to 0. So the total area can still be 1, even if it goes out forever, which is hard for people to imagine. But if I asked you like to paint inside of here, once you got to this little corner over here, you wouldn't need any more paint because you couldn't fit it in there anyhow. So it does technically still equal 1. So if I shaded in the whole thing, the area would be 1 underneath the curve. Okay, now the mean is 0 and the standard deviation is 1, so look the way I numbered it. I put the 0 in the middle, because the mean always goes in the middle. And then remember we've been counting by standard deviations to talk about what's significantly high or significantly low. That hasn't changed. So I'm going to add 1 standard deviation, and then another one, and then another one. Can I fit those on there? There, yeah. And what's my standard deviation in this case? 1. So I'm just going to add 1, and add another one, and add another one. That's where those numbers come from. Standard normal means you're counting by 1s. On our exam that we took, we were counting by other standard deviations. And then if we go back the other way, that's where that picture comes from. Now, see how I labeled this as my x-axis? We called them x's like we did before. When you're working with standard normal, to make sure it's clear that we're referring to standard normals, They actually call this Z. They call it Z to go with standard normal. We've seen Z somewhere before. Been a while. Z-scores. What were Z-scores?
How far from you?
Told you that. I heard you both at once. Go ahead.
Those are variance.
It has something to do with the variance, something actually with standard deviation, but how much you vary away from the mean. What did you say, Hector?
How far away from the mean?
Yeah, how far away from the mean. And it's not just how far, but it's how many standard deviations away from the mean you are. So for example, if I'm slightly above average height, I might be 1 standard deviation above the mean height for women. And somebody who's really petite, or maybe Christiana, she's a little bit shorter than me, maybe she's 1 standard deviation below the average height for women. Right? And somebody who's really tall, like the other Jill, you guys, she's probably 3, I don't know, she might be 2 or 3 standard deviations higher. She's 6 feet tall. I'd have to figure out what the standard deviation is, but she might be 3 standard deviations taller than the mean. So her Z-score would be 3. She's not 3 feet tall, but she's 3 standard deviations above or below. So the Z is just how many standard deviations away you are. So this is 1 standard deviation away, that's 2, and so forth. Okay, so the way we find probabilities underneath this curve is not the same as uniform because I don't have a rectangle anymore. Just look at my first example, then I'll mention what's up above there. Example 3a. Find the probability that the Z-score is less than negative 1.54. Don't ask why I picked that number. Where's negative 1.54?
In between negative 1 and negative 2.
Yeah, somewhere almost halfway between here and here. Approximately right here. There's negative 1.54 on the number line. And if I want less than that, I need to go this way, right? To the left. And if I shade under my curve, I get this weird little shape. Kind of looks like a triangle. It's not even a triangle because this part's curved. It's definitely not a rectangle anymore, though. We agree I can't find the area of that rectangle? I suppose we could approximate it with a triangle, maybe, but it's not a triangle either. So, but what happens is normal comes up so often that we actually have tables, which we're about to look at on our packet, and we have calculator functions that will figure out that area for us. Because we can't do length times width anymore. Everyone agree the shape's too weird? With calculus we could, but we don't want to do calculus today. That is hard enough. Okay, so right above example 3 it says finding probabilities can be found in 2 ways. Now it says table A2 in the back of our text, but table A2 is actually on, let's put it up there, on our packet page, I think it's 4. Yes. Page 4 and 5 actually of your statistics packet. Scary looking, but we're going to talk about how to use it. So when it refers to table A2, you can look for it in the book or you can look for it online, but you also have it in your packet. Sometimes it's easier to pull this out than to go searching for it in the book. This tells you how to find probabilities for a whole bunch of Z-scores. And we're going to discuss exactly how to use it, so no need to panic. Yes? Yes, you may. That's it. Page 4 and 5? Okay. Then we're also going to use our calculators, but first we're going to use the table to make sure we understand how those work. So find the probability that Z-score is less than negative 1.54. So first off, if I'm looking at this table, one side has negative Z-scores, one side has positive Z-scores. Which one do I want for this problem? Negative. Negative, right? Because I have a negative Z-score. So I'm looking on page 4. Notice what's shaded up at the top here. I don't know if yours is shaded or not. The picture at the very top, it should be shaded from that Z over to the left. It should be a little bit darker. Similar to this picture here, actually. Going and shaded to the left. And notice right next to where it says table A2, it says standard normal distribution, cumulative, which means the total area to the left. This table always gives you the area to the left. You might want to highlight that to the left, underline it, circle it. Some people go up here and color this in and shade it darker so you can see it's to the left. The reason that matters is I could have asked for something to the right and the table wouldn't have done it. But we'll talk about how to do that in a few minutes. But it's important to know that table always gives you area to the left. Good there? So now that we know it's area to the left, isn't that what we want? We want the area to the left of negative 1.54. We want the probability that z is less than negative 1.54, which, remember, the probability is the area. We want the area to the left of negative 1.54. Those are the same things. The area is the probability. So here's how it works. We have to find the z on the edge of this table. We start by going down the left-hand side. I have negative 1.54. What's the problem with going down that left-hand side? Yeah, it only has one decimal place, not two. So let's go down to the negative 1.5. So negative 1.5 is a little bit more than halfway down on the left-hand column. You guys following where I'm pointing here? And then, see these numbers going across the top? The 0.00, the 0.01, that's giving you your last digit. What's my last digit?
4.
4. That's like adding 0.04 onto the end. So I'm going to go down to negative 1.5 and over to the column. I'm sorry, I'm turning around and looking at the same time. Over to the column, I'm holding my hands in both places. Negative 1.5 on the left and 0.04 on the top. And go across to where they meet. And what's the number you see right there?
0.0618.
0.0618? Do you agree with him? Before I say anything else, is there anyone who wants to know where that number is? Either ask me or your neighbor to point to your table if you don't see where it came from. If you ask for help on this on my stat lab, it'll pull up this table and say, look at this. You need to know how to read it. Everyone found this on their own? You guys are good, or quiet, or shy, or scared. Oh, it's good. What does this mean? 0.0618.
That's the probability.
That's the probability of
Getting less than 1.
getting less than negative 1.54. It's around 6%. I've shaded, now my picture's a little bit off from the one you have. Yours should actually be skinnier than mine. We should have shaded around 6% of the total area. Mine looks a little bigger, but that's because I drew it by freehand. You okay with that? No questions? Yes?
There's another problem that shows that the z-score is less than negative 1.54. What if the z-score is 1.54?
Ah, good question. So he says if it's less than, we can do that. But what if it's exactly negative 1.54? It turns out that that probability is 0, which makes no sense. Because how many numbers are there on this number line? 7?
7.
7?
Infinite.
Infinite?
Yes.
That's a big difference from 7 to infinite.
Infinitely 7.
Infinitely 7. Never heard of that. It goes on forever. And let's just talk about between 0 and 1. How many numbers are between 0 and 1? Hella. Hella, she says.
A lot.
A lot. Because you could say, well, 1/2 is in there. And so is 1/3. And so is 0.00984. Right? I mean, I'm just picking numbers between 0 and 1. How long would it take me to write down every possible number between 0 and 1?
I don't know.
Forever. I could never do it, right? Because I could always come up with another one. So there's an infinite number, way more than 7. There's an infinite number of points on here. So if I say there's an infinite number, guess the one I have, how likely are you to guess the one I've just made up? 0, because there's an infinite number and you'll never guess the right one. So technically it's 0 to get a specific one. So with normal, we always talk about above or below, because it's hard to get that exact point. But what if there had been a greater than problem?
Your chart.
What if I just change this problem? I'm going to add a little problem right next to it or underneath it, maybe off to the side if you can squeeze it in. What if I had said z greater than negative 1.54? Add this problem. It's not in your notes. I claim that you already have the probability skills to answer this question. Yes, sir.
Subtract the number from 1.
Aha, he wants to subtract this number from 1. Why does he want to do that? Yeah, why does he want to do that? It's the complement, right? Either you're less than this number, or you're bigger than that number. It turns out Anthony's a genius, and he just let us all in on it. Either you're less than negative 1.54, or you're higher than negative 1.54. So if I wanted the area to the right, I would still look this number up on the table, but then I would take 1 minus that, which is 0.9382.
Yeah.
When you have a greater than problem, your table won't give you the answer directly. It will always, that's why I was so careful to point out it gives you the area to the left. If you want the area to the right, you're going to find the area to the left on your table, and then take 1 minus to get what's on the right. Okay with that problem I added in there? Yes, sir.
What if it was z is less than or equal to negative 1.4? Is that literal?
It's the same whether it's less than or equal to. Because again, getting exactly that doesn't make any difference. So whether we write less than or equal right here, same answer. Because it's, again, impossible to get the exact number.
Can you say that again? You said if you have a greater than question.
So oh, not the part he asked, the part before that. So when you want to do a greater than, you're still going to look up the number on your table, but the table will give you everything to the left. So you're still going to look that up. So if we had never done the first problem, and I just asked you the second problem that I made up here, I would have still looked up negative 1.54 and found this 0.0618. I, of course, would have drawn the picture so I would see that I looked up area to the left. But now that I have the area to the left, because it's greater than, I'm going to take 1 minus that to get the area to the right. You finish writing that down while I was talking about it? Okay. Still good? Okay, let's do question B. Question B. Notice I keep drawing the little picture off to the side there for you. Eventually I'll stop drawing them on your notes. You'll have to draw them on your own. You'll get fairly good at it eventually. Mine are not always perfect either, but just as long as you have the general shape, it helps. So question B has the probability that z is greater than 0.5. And here's my picture again. What do?
Find the complement and subtract from that.
Yeah, we're going to have to start with the complement, but before we even do that, I'd like to finish the picture. Again, I will never force you to draw the picture. Some of you can do it without the picture, but if you go into the math lab and ask for help on this, the first thing they're going to ask you is, where's your picture? Because if you have a picture, you can see if you're going right or left, if you want the left hand, the right hand. You can visualize whether or not your answer makes sense in terms of how big of an area it is. So I like to draw the picture. So what should I do? Between 0 and 1 is 0.5. Here's 0.5 right there. And since it's greater than, everything to the right. So I want everything to the right. Looks like a fairly good sized area. A little less than half. So it looks like to me. Okay, how I'm estimating that, just kind of looking at what the size should be. So then, what am I going to do? Look it up on my table. What number am I going to look up on my table? 0.5, but then how far over do I go? Yeah, it's 0.50. If you don't have another digit, it's technically 0.50, right? So when you look up 0.50 on your table, I don't have mine in front of me, I'm going to trust you guys to look it up correctly. What number do we find? 0.6? 6915? Pause. Who needs me to point at their table for them? Yeah, it's positive. Yeah, be careful. Positive, she's on the wrong side. Because it's a positive z-score, you have to look on the positive page.
No.
Anybody need help looking that one up? We flipped over to the positive side. What'd you say? It's weird?
Yeah, isn't it supposed to be like shaded from like all the way down? Like,
Because it always gives you the area to the left. So let's talk about that. He's saying, hey, on this one, it's still shaded to the left on the positive page. It always gives you the area to the left. So when we just looked up that number, he says, this is weird. What is that number? In terms of my picture. It's everything to the left of 0.5. What the table just gave me is all this.
But that's why we find the complement, right?
And that's why we find the complement. And that's why I can't stress enough. The table will always give you the left, even if that's not what you want. So is this my answer?
No.
No, thank you. That's a very emphatic no. No, Jill. How am I going to find my answer? 1 minus that, which is the complement. So you have to know, the table even tells you, you have to know that that table always gives you the left. So if I want the right-hand side, the blue one is the one I wanted here, I have to take 1 minus that, which is 0.3085. Which is close to 31% that I've shaded here. The blue part is around 31%. If you hadn't subtracted it from 1, and you thought, I'll just write down the answer of 6915, that looks reasonable. Based on the original question, let me erase the green here. Based on the original question, how could you have known that 6915 is not the right answer? Right, because this picture is less than half of the area. And what's this? 6915 is more than half. So something's definitely wrong. Make sure you look at your picture and see if your answer makes sense. You can't have an answer of shade less than half and have an answer of more than half. It wouldn't make sense, right? Okay, ready to do the last one? Let's do the last one on the page. Z is between -3 and 3. Between -3 and 3. I'm going to do it on top of this one since I already have it drawn here. It looks like almost all the area. Looks like. Is it all the area? Is it what? Nobody's answering me. Does that mean you don't know?
No,
No, it's not what?
because it never touches, right?
Because it doesn't technically touch. And if you look closely with your fine-tooth comb or your magnifying glass, between -1 and 1, or excuse me, -3 and 3, is starting here at -3, going all the way here to +3, and everything in between. It's almost all of it. But I'm going to exaggerate these. Do you agree there's a couple little slivers over here that get left out? These little slivers over here get left out.
Can we round it to 1?
Could we round it to 1? Technically it would round to 1. Who remembers the empirical rule from chapter?
0.05%.
No, not that one. It had to do with 1 standard deviation, 2 standard deviations, 3 standard. Yeah, what do you remember?
It was 99.7% of data values are within 3 standard.
Ah, did you look it up or you remember it?
No,
Okay, good. Oh my, that was impressive. Oh, I thought he was reading. It was, if you were 1 step away, it was 68%. If you were 2 steps away, it was 95%. And if you were 3, it was 99.7. That was it's called the empirical rule. I called it the 68, 95, 99.7 rule. Well, since we are 3 steps away, the answer should be around 99.7%. So we're going to actually use the table to see if it really is. We'll see where that number came from. So from that rule, I think the answer should be 0.997, 99.7%, just from past experience with the empirical rule. So the question is, how the heck do I find this on the table? I have 2 numbers.
Find both and find both.
Ah, so we're going to find both and then figure out what to do from there. So let's start by just looking up the -3. -3.00, right? Because you have to have your 2 decimal places. We agreed. -3.00 is what we're looking up. Can you see this red, Nick? I forgot I'm supposed to use the red. And what'd you say the answer was for that one?
0.0013.
0.0013? Did we agree with her, or do we need to see where that came from? You agree with the hand signal.
We want the other side.
Well, we want the other side, yeah. Where is this 0.0013 on my picture? To the left of -3. It's this little sliver over here, right? This little tiny area right in here that we don't want is 0.0013. Okay, so we'll hold that thought for the moment.
We can do 1 minus that.
Yeah, but if we did 1 minus that, what would I get?
Everything.
I'd get everything above there, and it would go past here.
Yeah.
Oh darn. My sister would say, oh dang.
We have to find the line, like the 3 and positive and
She's thinking ahead. She's, I think we better look for the one for 3, and maybe we have to do some subtraction. So let's talk about that. If we look up z equals positive 3.0,
0.9987.
say it again,
0.9987.
9987. So now you're looking on the positive page at 3.00. Hang on a minute while people are looking. That's not it?
no.
No? Let's see. Break the tie. What do we think it is?
Just kidding.
Just kidding?
Yeah, my bad.
It's okay, she just wanted me to practice using my table too. Thanks. I got it right too. We all agree now that it's 9987. Everyone's like, what did I do wrong? What is the 9987?
Everything from 3.
Everything from everything to the left of 3. I wish I had another color. I guess I could use blue. Everything to the left of 3. So that means it starts here. It's all this green stuff and this little red piece, which is now going to be purple. Do we agree it's everything from 3 all the way over? But I don't want this little piece. So I subtract it. So this is everything left of 3. The 0.0013 is the piece left of -3. That's this little red piece over here. So we agree that if I take this number, which is everything from everything from +3 over, and subtract the little red piece, I'll have exactly my original green one. If I subtract those, we get 4799. 0.9974. So remember Liam reminded us of the empirical rule. He says it should be 99.7. It's actually 99.74 to be exact. They had rounded it when we talked about the empirical rule way back when. So this is the answer. Let's refresh what we just did. When you're talking about between two numbers using your table, you find the area below the largest number using the table. Everything below the left of the largest number, that's what we have here. And you subtract everything below the smaller one. So that cuts off that other piece. And that will be your total area, your total probability, which is not 100%. Remember Hector said, can we just round to 1? It does round to 1. But technically it's not all the area. It's 99.74% of the area. There's little slivers that got left off. Questions? Okay, let's go ahead and take our break. We'll come back in 10 minutes, then we'll talk about how to do these same questions with our calculator. See which one we like better, the table or the calculator. Already, have a look at the bottom of page 71 where it tells you how to do these same problems with your calculator. So anytime you're working with the normal distribution, you have two options. One is to look it up on the table, which we just did for all three of these problems. The other option is to use your calculator. So at the very bottom of page 71, you first go to distributions. What did we use that for before? Why did we go to distributions before? For binomial PDF or CDF? It's yet another distribution. Binomial was a distribution, so is normal. Uniform's not in there because uniform's pretty easy. We're just doing rectangles. But so you want to go to normal CDF. That's the one we're always going to use, normal CDF. I'm not pulling up my calculator. I want to make sure that you can all get to that screen under distributions where you see normal CDF. And when you find normal CDF, squeeze it in right here, you always put in what I call the left, the right, the mean, and the standard deviation. Now some calculators call this, they call it upper? No, lower and upper?
Yeah.
Lower, upper, mean, and standard deviation. So the lower and the upper is describing when you're talking about your region. I'm going back to the last problem we just did before the break. Remember we did between -3 and 3? For this shaded region, the green one was my original region. What's the lower number? -3. And the higher number was +3. So if I want to do this problem on my calculator, I would do normal CDF with my lower number is -3. My upper number is +3. My mean is 0 because we're dealing with standard normal, remember? 0 and 1 for standard normal. Every time you have z's, it's 0. And the standard deviation is what?
I got error.
You got error? I want to see what you typed in. If you have the one with the pretty screen, it might want to do it on 4 different steps. You hit the minus instead of the negative. The negative. It's really grouchy about negatives instead of minuses. And I've gotten pretty good at recognizing that because the negative is slower.
Okay.
Try that and see if it works.
Yeah.
Yeah? Yes, Christy?
So we're doing C, right?
Yeah, I'm just doing part C, the one we just did before the break, between -3 and 3.
And the answer is 99.74.
Uh-huh.
But when I put it in my calculator, I got 99.73.
Yeah.
Uh-huh. So the calculator says 99.73. That's not the same as this. So here's the deal. The good news is that you're not always going to get the exact same answer, and my stat lab knows that. So the table was created years ago before we all had these high-powered calculators or computers that could do this for us. And so someone actually created these tables years ago so that we could find these probabilities. There was no nice way you could grab a computer or a calculator. And so a lot of things got rounded along the way. So this is an example where it got rounded along the way. Now that we have these high-powered calculators, it can be much more precise. This is the precise answer right here. But if this problem was on an exam or on MyStatLab, you could type in this one, or you could type in that one, and it will give you the correct answer. It knows that you might get different answers for technology versus not technology. If you're doing problems in the book and looking up answers in the back, it would say something like, the answer is 0.9974, and then in parentheses it would say technology 0.9973. So it knows that if you're using a calculator, you're going to get something slightly different. And what's funny is, sometimes they're off even more. Like maybe this is 9974 and this one's 9971. It wouldn't take an answer in between those. Like you couldn't say 72. You'd have to either put the 71 or the 74 because it knows that you're doing one way or the other. So they won't always exactly match, but whoa, they should be very close like these are. I'm glad you brought that up. I forgot to point that out. Everyone okay what I'm talking about there? The calculator will always be exact. If this is on an exam, if this problem was on the exam, you would either say, I'm using the table, and you would show me this work right here, and I would give you full credit. I could see what you looked up on the table, and you got this answer. If you said, hey, I'm using my calculator, I did this, I'm giving you full credit. The main thing is I want to know how you got there. Did you use your calculator? Did you use the table? And then I can tell which answer you should have. We okay there? Okay, let's go back and do A and B. Those were a little bit different than what we just did. Okay, can I do B first since my picture's right here? My picture's right here for B. Normal CDF wants the left and the right, or the lower and the upper. What's the lower and the upper, or the left and the right?
We have to find the complement of the number of layers.
Well, for my shaded region, my blue region here, I want the number on the left and the number on the right. Or the lower number and the upper number. So what are you saying? It's 0.5 for sure, but it doesn't stop at 3. It goes past 3. Right? I mean, technically, it goes way out here. We just can't tell. It's just so skinny. It goes to 0.5, and how far out here does it go?
Infinity.
Infinity. Well, we can't put infinity into our calculator.
Yeah, no.
We have to have an upper. We can't do it without one.
Pi?
Pi? Pi's not big enough.
Oh, what?
Pi's only 3.14. It's barely past here. But what we have to do is we have to actually tell our calculators a little white lie. We can't put infinity in there. And so what we do is we say we have a number that's so far out on this number line that everything past it's going to round to 0. So we just pick some large number. Some large number. I usually just hit a whole bunch of 9s. 9, 9, 9, 9, 9, 9. How many 9s you want. Because it's already close to 0 after I pass about 5, to tell you the truth. Anything past that really large number will be the upper. And a lot of times I will only write 999, but when I type it into my calculator, I just hit a bunch of 9s and I don't really count how many. So we would put normal CDF, starting on the left at 0.5. I'm just going to pick a really big number for the right. So you have to make up the really big number. The really big number that you make up does not have to match mine. It just has to be way bigger than 5. And then my mean and my standard deviation. Try it. Try a different big number, different than mine. We should get the same answer. This is some big number. You could use mine or you could make up your own. Pi's not quite big enough. Pi might even work. It's pretty close. But it's bigger than that. What are we getting? 3085?
Yeah.
Yep.
Exactly the same answer we got last time with the table. Did somebody try a different big number? Or did everyone use mine? Nobody wanted to be creative? Put a 10 in there. Somebody put a 10 right here instead of the 9999. See what happens. Change this to a 10. It's the same. Why? Why is it the same? Why is it the same? 10 is roughly here. Right here's 10.
This is smaller.
Yeah, it's so small after that that the area rounds to 0. So even 10 would have been big enough. The problem is once we get different means and standard deviations, the definition of big changes. If I'm going to tell you I'm going to give you a big raise, 1 cent isn't exactly big to you, right? But if you only make 1 cent and I give you 1 cent, that doubles your money, right? So it depends, it's all kind of relative. So you just want to pick some really huge number that's off your chart, wherever your chart might be. That's why I just picked a huge number. But technically in this case, 10 would have worked. Okay on the big number part? So what are you going to type in for part A?
Negative 1.54, and then 15, and then,
You're close, Kirsty, but the left and the right and the lower and the upper matter. So which one comes first? Let's draw my picture. It was negative 1.54,
mm-hmm.
and it was to the left over here. So we're talking about,
Oh, so it'd be a negative.
aha. The negative number has to come, the big negative number has to come first, because I'm talking about from negative 1.54 all the way this way, way out there. Way out there, I can think of it as an arrow, just keeps going. What number's on the left?
The big.
Some negative in the big number, right? This is the left, this is the right. This is the lower, this is the upper. If you put them in the wrong order, you're going to get a negative probability, which would not be good. So what do you want to type in this time?
Put -5.
You put -5? Let's see if that's enough. -5. He picked 5 as his big number. It's okay, we're going to see if it works. What comes next?
Negative 1.54.
Negative 1.54. The mean and the standard deviation. Somebody picked a different number than Kevin? He chose -5. Somebody else chose a different one?
Negative 99.
You did -99? Big negative number. Here or here? Let's see if the answers came out the same. What did we get? What did you get, Kevin?
10617.
0617? You got the same thing? So even in this case, -5 was far enough away that everything out that rounded to 0. After that rounded to 0. I usually go a lot further than -5 because there'll be a situation coming up where -5 isn't far enough away. So you want to go way off the edge of your number line. In this case, that's just about as far as you could go before the answers would change. Yes, Kirsten?
I did mine when I was saying to do the negative 1.54 first,
Mm-hmm.
and then I put in just a random different number and then the 0 and the 1.
Mm-hmm.
Just realized it gave me the complement of the 0.0618.
Okay, I like it. I'm going to write this in red because it's not for this problem. So here's what she's telling me she did. She started with the negative 1.54 and then a random big number,
Yeah, I put 15,
15.
and then 0 and 1.
Can somebody tell me what she found?
The greater than.
A greater than. You found everything, Kirsty, starting at negative 1.54, going out to 15. So if you look at my picture, you're starting at negative 1.54 and going that way, towards 15.
Right. I was just saying I answered the second part of that question when you had us flip the
Oh, you're doing the,
side, so
oh,
it gave me the complement.
yes. So as long as you know which one you're looking for, you'll be fine. The important thing is if you wanted the original one, the one on the left, you had to start with the lower number and then the upper. Sounds like you've got it both ways though, which is good. Comments or questions about what to put in your calculator? Yes, ma'am.
Well, on the calculator, it says 0.606178.
Ooh, so we have to round that. Thank you, let's fix
I
that.
used negative 999, so I'm not sure what it is.
Did everyone just cut it off and not round it? And Ariana's the only one that noticed it should have been 0.0618? Yeah?
I put 06.18.
Oh, okay, I just heard 7 when I wrote it down. People who said 7, do we agree it rounds to an 8?
Yeah.
We always round. If you don't round it, you'll get it wrong. You can't just cut it off, you have to actually round it. Thank you for paying attention to that. Way in the corner, can you see anything? Other comments or questions? Okay, so let's do an application problem then on page 72. We have scientific thermometers. I'm on example 4, page 72. Scientific thermometers are designed to read 0 degrees Celsius at the freezing point of water. So if all thermometers are perfect, when you put them at the freezing temperature of water, they'll say 0, it's 0 Celsius. But not all thermometers are perfect. I mean, we know that all the time, right? You ask somebody what the temperature is outside, you can find 5 different answers. So they're not all the same. So it says they're supposed to say 0, but tests have shown that these thermometers sometimes have readings above and below 0, with a mean of 0 degrees and a standard deviation of 1, and assume that these readings are normally distributed. So without reading any further, what are they telling me?
Make a chart.
Make a chart that looks like that. The same thing we've been doing, right? They say they're normally distributed, so we know we have this graph. They're telling me the mean is supposed to be 0, and the standard deviation is 1. You see all that in there? They're essentially telling you that they're dealing with the standard normal. So my picture has not changed. We have to now draw our own. So all I did was draw the picture, I haven't even looked at the question yet. Everyone see how I knew from those words, though, that it was the standard normal situation? Yeah? Okay. Find the probability that a randomly selected thermometer will show a reading higher than 1 degree Celsius. These numbers down here now represent the temperatures, right? That's what we're talking about. They're supposed to say 0, but there's this deviation.
Did we do 3 and -3 because it's got to be 3 or more standard deviations away for more than 2?
We really just mark it up to 3 and -3 because after that there's really not much area left. I mean, technically you could go all the way out to -10 to 10 if you wanted to. The problem is if you did that, it would kind of look like this one, where there's just not much there. So we pretty much just kind of draw to -3 to 3 because that's almost all of it. But you could stop marking it at 2 if you wanted to. It's just trying to estimate what it looks like. What helps me is, of course, the 0 goes in the middle. And then see where it's like, feels like it's going, it's really getting steeper and steeper and then it slowly gets flatter. Right here where it kind of switches, like at the steepest point, is where the 1 usually is. So then I just mark it from there. But I am not going to grade you on how perfectly your picture is drawn. But that's why we go -3 to 3, just because that's almost all of it. And you'll notice that I can start getting sloppier and sloppier. My little tails over here, we call these little tails on the edges, they start curving up, which technically they don't do. I just get sloppy when I draw them. And sometimes you'll actually make them touch too soon, but as long as you understand that they don't, then you're fine. Okay, so the question was, probability that a thermometer will show a reading higher than 1 degree Celsius. What do I want to do?
Infinite your calculator.
Okay, but I want to draw before I put my calculator, please. What am I going to draw?
From 1 to your left.
1 to the left?
1 to the right.
1 to the right? Uh-oh, controversy.
Both.
Both? What is it asking for?
It wants to the right. It was
Higher than.
higher than what.
So let's always, I always like to draw what they want. So they want everything to the right. So this is what they want. Everything to the right. You agree with that, Evelyn? If I was going to use my table, what would I do? Bless you.
You would start with negative.
I would start with looking up 1. I still look up my number 1. Did you say -1, Kirsty?
No, I said -3 because I'm.
Ah, different problem. But we're talking about 1. So I would look up 1.00. Bless you. I would look up 1.00 on my table because that's my z. So we'd go to the positive page. Positive z's. We would look up 1.00. Tell me again. 0.8413. Give everyone a chance to find that on their table. What is the 8413? That's everything to the left. This side over here is 8413. Everything to the left. Remember, the table always gives you the left. So how am I going to find the right?
Subtract by 1.
1 minus that. Complement, right? The other side? 0.1587. Yes?
Could you also go faster by like just looking at the left side, like a -1, so probably that, and then select it?
So a lot of people like to do that. And I'm going to not necessarily recommend it because some people can't make that connection as easily. But if you can, I have no problem. What he's saying is, if you're talking about 1 and up, do you all agree that's the same area as -1 and down? So he says, I'm just going to look at the -1 and that'll be the same answer. I don't really have a problem with that as long as you're doing it correctly. But I don't like to show it to you the backwards way because then people are like, why are you doing the opposite problem? But technically it does work. You know it's the same size as this one, so just do this one. Then you don't have to subtract. Or you can use your calculator because most of us prefer those to the table. What do I put into my calculator for the original problem here? Starting at 1, I can drop it in there.
Huge number?
Some huge number. I think I'll do 999. 0 and 1. Because I'm starting at the left, stopping at some really big number way past there, 999. And what does that one give me? Is it round to 6 or round to 7? So it's the same. Either way. If this problem's on an exam, you can do it either way. I want you to do B and C. Well, I want you to do B because I need to help you with C. I want you to do B. And then we'll do C and D together. I'll draw a picture for me. If you did it already, try it the other way. If you used your table, use your calculator. And if you used your calculator, use your table. See if they agree. There will come a point where we need the table for a couple things. So you might want to get used to it. table's a little bit more tricky.
Came up with the same answer.
Same answer both ways? That's always a good sign. Okay, so who wants to tell me how one way they did it? Hold that thought, Hector, see who else did it. You got Hector's all over it today, so's Kirsty. Somebody new want to help me out? Anybody? Feeling confident? Nobody?
Well, I can tell you the CDF.
Okay, tell me what you have a CDF.
First number was negative 0.5.
Right, normal CDF here first. Normal CDF, negative 0.5,
Then 0.5,
then positive 0.5,
and then a 0.
0 and a 1. Oops, too many comments here. And what was the answer?
0.383.
383? Did it have one more digit?
It rounds.
Rounds to 0? Okay.
Yeah.
Quite often in this chapter, they'll always ask you for 4 digits.
For 4? Okay.
Because the table gives you 4 digits, so they'll ask you for 4
yeah,
digits. Questions on that way? Okay, so how do we use the table? I know Kevin did it both ways. He knows it. Did you use the table, Hector?
I use table and then
Okay.
I just did CDF, and I just got the easier way.
Yeah. Yeah, the CDF is much quicker than the table. When you have the 2 different numbers, the table's a little bit more work. So if you use the table, what do you have to do?
You gotta find the two probabilities first of everything below negative 0.5, and then everything below 0.5.
So you have to find the probability for this one and the probability for this one, and do what with them? Subtract them. So if you're doing the table, what are the 2 numbers that you end up subtracting? The first one is
0.6915 and 0.3085.
you have to look both of those up on the table, and you still get exactly the same answer? The good news is I will never force you to use the table or force you to use your calculator. You can do either way. Yes, sir.
So when you subtract the 2, they give you 0.383. Do you have to put a 0 on there?
No, you don't have to.
Okay.
It's a habit for me when we get into normal to always write 4 digits, because if you had looked this up on the table, it would have had 4 digits and so on.
Right, right.
But it's equivalent to just write 0.383.
Okay.
We got that one? Okay, here's the problem. C and D are kind of backwards. They're a little bit more challenging. A little bit more challenging. Question C says, what temperature corresponds to the 80th percentile? And I even have a little note there about working backwards. And it tells you what to do in your calculator, but I want to draw the picture first. What does 80th percentile mean?
0.8.
0.8?
80%.
80% are
Temperature.
80%. 80% below. Remember percentiles? Like if you were in the 80th percentile on a test, 80% of people scored less than you. So if you're in the 80th percentile for thermometers, 80% of those thermometers had a lower temperature, or lower than that. There's some temperature, and 80% of them are lower. So just visually, here's the same picture for my thermometers. Visually, where do you think I might be so that 80% of the area is lower? Just by looking.
And 1.
Maybe around 1-ish? She thinks maybe right here, question mark. Because, why?
Everything below it.
This looks to her, this area looks to be about 80%, 0.80. That's why you have to recognize the whole thing as 1. The answer isn't 1, by the way. We're guessing. We think it's around there. Right now we're just guessing visually of what number gives me exactly 80% to the left. You okay with the picture in terms of the question? And the answer might be a little more than 1, might be a little less than 1. We don't really know what it is right now. What is that 0.80? Is it a probability?
I mean, it's a,
Yeah, it is a probability because it's the area. Remember, the area is the probability? So when you look at your table, where are the probabilities on the table? Where did we get the probabilities off the table?
positive.
In the middle. The middle gave you the probabilities. The edges gave you your z's, the middle gave you your probabilities. So let's start off, first off, do we think we have a positive or negative z-score? It's definitely, well, look where we are, Kirsty. What is the z that we're guessing?
Oh, positive.
That's we don't know exactly what it is, but if it's 80%, it's got to be on the right. So that's a positive z. So we're going to look on this positive z page. And here's where we have to take a little bit of time searching for the probability as close to 0.80 as we can get. So we're looking for a 4-digit number that looks as close to this as we can get. Searching and searching for the closest one in the middle of this table, because we know the answer is supposed to be 0.80, so we want the closest one. You think you found it, Anthony?
0.85.
Yeah.
0.85? That seems kind of big. Where are you?
0.8023.
That's what I said,
Well,
0.80.
but
The number on the chart is 0.85.
I think.
Oh, you're giving me the z. Yeah, tell me what the number is here, sorry.
Oh, okay.
The closest number you can get in the middle to 0.800. What number were you looking at?
The same one.
8023? I think there's something closer.
0.79 or 0.7995, right?
So there's a little controversy here.
Yeah, that's good to know.
So one person thinks this is as close we can get, and somebody thinks this is as close as we can get.
You would round the 7995.
They are looking right about the middle of the page, about a quarter of the way down, roughly here, if you haven't seen it yet. Do we all agree that those two numbers are fairly close to 0.8000? Which one's closer?
7995.
Why is 7995 closer?
Because like it says you round up. And then it would round up to.
It's only 0005 away. How far away is this? 0023. This is like 23 away, and that's 5 away.
Yeah.
So do you agree the 5 is closer now? Yes, sir.
I use inverse norm and it says use the z-score is 0.84.
Yeah, we're going to do inverse norm in a second. Do we all agree, though, that this one right here is the closest we can get?
Yeah.
This was close, but this one was closer. So now that we found that 7995, we want to look to the edges and say, well, what is that z that goes with that 7995? If we look over at the edges, I lost my place. I'm on the wrong side. No wonder I lost it.
0.04.
Starting on the left.
0.8.
Z equals 0.8 on the left, and then it lines up with the 4?
Yeah.
You have to look left and up to find that number?
Yeah.
What's that tell you about my picture? Is my picture right? Is this picture correct?
No.
Is this the number that cuts off 80%? 1? No. Where should it be? A little bit over here. So I'm going to adjust my picture. It's not at 1. It's at 0.84. That's the exact z right there that gives me the 80% to the left. What's that look for, Jenna? We found the 7995.
Yeah.
And we want to know what z gives you that probability.
Oh.
So we had to look on the edge, oops, I'm backwards now, on the edge, on the left and the top to see what that z was.
And that was the answer.
Say that again?
And that was the answer.
And that was our answer. What does that have to do with these darn thermometers?
Um,
80th percentile.
The temperature
So the 80th percentile, which means 80% of the thermometers, if I could say it, 80% of the thermometers have a reading that's less than 0.84 degrees. That's the cutoff. They're supposed to say 0. 80% of them are less than 0.84. Now, there's a nicer way to do this with our calculators than to work backwards on the table. That backwards on the table thing's a little tricky. The important thing is that you know you're working backwards. Why do I say backwards?
You start from the middle, put it out into the middle.
Yeah, but if I'm not using the table, why would I say I'm working backwards? I'm not want to talk about the middle. What makes this backwards?
You're only given the area.
Yeah, you're given the area, and you're asked to find the z, right? Where all the other problems that we did before this, where here's the z, find the area. That's what I mean by backwards. So normal CDF finds the probability or finds the area. If you have the area and you want to know the z, you're working backwards. And that's where we do what's called inverse norm. Inverse norm.
Did you say the normal PDF finds the area?
Yes, normal CDF, I'll write it over here. Normal CDF, which we were doing for all the other problems before this. This finds the area, which is the same as the probability. Area and probability are interchangeable. So this question, though, gave us the area by saying we know the probability is 0.8, we have an 80%, and asked for the z-score.
And that's what that will give us is the
And
invert norm.
That's what inverse norm will do. If you know the area and you're looking for the z-score. So inverse norm, I see we're out of time. Let's just start this one and we'll be good. I'll have to extend the homework on 6.2, obviously. We were going to start that today. What does it say on the page? What we put in the inverse norm?
You said the area and then.
Yeah, it doesn't just say area though. It says area. What do my notes say? I put them down and walked away.
What is it on there?
They're on the bottom of that same page. Or they're right there next to it, I think. Did I put it there? Or I didn't. Oh, I thought it was on there. No wonder you're not reading it to me. Okay. You have to tell it the area to the left. Always the area to the left. Even if that's not the one you're looking for. And then the mean and the standard deviation. And we are out of time, so I will extend the homework on this and I will finish this next time. But you should be able to get through most of it. I will pick right up left time, right here next time. And I will extend the homework because it's not there. I will still quiz you on the part we've covered though.